So hello guys, once again I welcome here all of you in this marathon session. Today we're gonna start a new subject actually, that is environmental engineering. In the previous marathon session, we have covered all all portions of transportation engineering, where we covered highway engineering. In there we covered geometric design and highway materials, pavement design, airport engineering, railway engineering, and yeah, one thing left there, that is traffic engineering. We'll cover it very soon, but for right now we'll discuss the environmental engineering. So our first chapter basically in environmental engineering is water demand. Okay, so today we're gonna discuss about water demand. So yeah, let's go. Water demand. So first thing first in this water demand is calculation of fire demand. Calculation of fire demand. For this we have formula that given by Kuchling, given by Kuchling. So basically, it is called Kuchling formula, and its formula is something like Q is equal to 3182 under root P, where Q is water required. Uh, sorry, Q is required water required, and P is population. Okay, so this formula is given by Kuchling. Let's we have another formula for this, that Freeman's formula. One Kuchling formula and another one is Freeman's formula. Freeman's formula. So for this we have formula that the Q is equal to 1 1136 bracket P plus 5 P by 5 plus 10. Okay, again here this is water required and P is for population. Okay, so this is given by Kuchling and Freeman's formula, and let's move on to next thing in calculation of fire demand, that National Board of Fire. What? National Board of Fire. Basically, National Board of Fire, yeah, fire gave concept, gave thing for calculation of fire demand for central congested high valued city and for residential cities. Okay, so first we gonna for central congested high valued city. For this we have a formula basically in condition one. Sorry, if we have population less or is equal to 2 lakh. Wait, if we have population less or equal to 2 lakh, then we have formula, it is something like Q is equal to 4376 under root of P. Okay, and if we have a population greater than 2 lakh, if population greater than 2 lakh, then we have formula. Here one more thing, 1 root P also in this formula. If we have a population greater than 2 lakh, it is we have a water limit that 5400 liter per minute. We need this much amount. Okay. And for second fire, it gonna be increased to 9100 to 36,400 liter per minute. And for second fire, it gonna be something 9100 to something 9100 liter per minute to 36,400 liter per minute. Okay. So this is about this is for central congested high value city. Let's move on to next thing, which for residential cities. So for residential city, residential city. So if in residential cities, if there is a small building, then we need what about 2200 liter per minute, 2200 liter per minute. And if we have high building, then we need water about 4500 liter per minute. Okay. And for high values apartments, this value gonna be increased to 7650 and to 13,500 for high values apartments. This increased to 7650 liter per minute to 13,500 liter per minute. 13,500 liter per minute. Okay. And for three-story building, it gonna be increased to 27,000 liter per minute for three-story building. For three-story building, it's gonna be increased to 27,000 liter per minute. Okay. So this much amount we need. This much amount of water we need. Okay. Let's move on to next thing. Next formula actually. That's called Boston formula. What it called? Boston formula. Boston formula. Boston gives formula that Q is equal to 5663 under root of P. Okay. So this formula is given by Boston. This is it in for calculation of fire demand. Let's we need to go to the next thing, which is maximum daily consumption, maximum hourly consumption, maximum weekly demand of water, maximum monthly demand of water. Okay. Let's move on to that thing. So before move to maximum demands of water, let's see one more thing, that the per capita demand. What is per capita demand? Per capita demand. Basically, per capita demand is equal to total yearly water requirement. Total yearly water requirement. Total yearly water requirement, obviously in liters, upon 365 days, 365 into design population. Design population means how many populations that thing is designed, for how many population of that thing is designed. Okay, so yeah, this is about per capita demand. Let's move on to our maximum demands. So for maximum daily consumption, we have a formula that for maximum, let's do this in next page, so it will be better there. Yeah, maximum daily consumption, maximum daily consumption, the formula that 1.8 into 1.8 into average daily consumption, average daily consumption. Okay, and for maximum hourly, basically it is denoted as q, average daily. And for maximum hourly consumption, it is 2.7 into q by 24. Okay, so 2.7 into average daily consumption divided by 24. 24 for what? 24 for what? Because this we need to calculate maximum hourly consumption. And for maximum weekly demand is 1 1.48 of average weekly demand, 1.48 of average weekly demand. Okay, and for maximum monthly demand, last thing, that maximum monthly demand, this value is 1.28 into average value of average monthly demand. So remember these values, because it will help a lot in numericals. Okay, mostly this one. Do remember all these value, but especially this value is help you. This value gonna help you a lot in your, while you solve, go for the numericals. Okay, and one more thing in this, that coincident draft. What is coincident draft? So basically for coincident basically it is came in your numericals, that there is a last point where they'll ask that what is coincident draft of that. So we have formula for that, coincident draft is equal to your maximum daily consumption plus your fire demand water. So so total water that for maximum daily and fire demand is sum of both the things is equal to coincident draft. Okay, so this is all about calculation of demands of water. Let's move on to next thing, that is population forecasting. Population forecasting. So yeah, basically in this population forecasting, basically we have 2 to 3 methods that to to calculate to calculate increase in population with respect to a number of years. That first method is arithmetic increase method, the second one is geometric increase method, and third one is incremental increase method. Okay, so let's go for first thing, that is arithmetic increase method. Arithmetic increase method. In this we have formula that Pn is equal to P naught plus x n bar, where our n is number of decade between now and future. Number of decades between now and future. Yeah. Okay. Do remember that here is decades, not year. Okay. That is number of decades. That means 10 years. So that is number of 10 years between now and future. And our x is average x is average population is in known decades. X is average population in known decades. Okay. So yeah, this is all about the arithmetic increase method. This basically P naught is present population, and N is Pn is the that year's population which we required to calculate. Okay, so let's move on to our next method, that is geometric increase method. Put it here. Yeah, that geometric increase method. In this we have formula that Pn means that population for the year which required and P naught is our present population, is equal to nx bar plus n plus 1 on 2. Here also this is n, this is x bar. Do remember that. Basically it both look same, so there will be confusion for you. Let me write it once again. N, and this is x. Okay. Here also this is n, this is x bar, and here n plus 1, n plus 1 by 2 into by bar. Okay, and you guys are already aware about n x bar and pn and p naught. One new thing here is that by bar. So by bar is average of incremental increase or average increase in a column. Okay, so by bar is shit man by bar is average of incremental increase or average increase in column, increase in given column, is in column. Okay, so yeah, this is all about geometric increase method. Basically there is a one problem. This is not that which I recall, that this formula is not for geometric increase method. This formula is basically for incremental increase method. So in flow I write this formula. Basically it is incremental increase method, not geometric increase method. Incremental increase method. Okay, so yeah, this formula for incremental increase method. Let's move on to our next thing, that geometric increase method. Yeah, so geometric increase method. Geometric increase method. So yeah, in geometric increase method we have formula that Pn is equal to P naught 1 plus k by 100 to the power n. Okay, you guys already aware about this pn, this p naught. Okay, and a new thing here is that k. So we have formula for k. Basically k is a growth rate per decade. Okay, so we have formula for k. You have to calculate k is from k1 into k2 into k3, so on to km. Wait, to the m. And also you'll calculate k from p under root p2 upon p1 minus 1. Okay, here this k1 k2, here this k1 k2 k3, here k1 k2 and k3. Basically this is a percentage increase in population between decades. These are percentage increase in population between decades. Okay, and what are k is growth rate per decade. Growth rate per decade. Okay, so this is all about our three methods for population forecasting, that arithmetic increase method, incremental increase method, and our geometric increase method. Okay, so let's move on to next thing, that decrease growth rate method. One another method of this, that rate method, decrease growth rate method, decrease growth rate rate method. Okay, in this we have formula that pn is equal to pn minus 1. How? Pn plus pn minus 1 plus r naught minus n bar r dash upon 100. Give me a second. It's at pn plus pn is equal to pn minus 1 plus r naught minus n r dash upon 100 into pn minus 1. Okay, where this r naught is growth rate of last decade, that is, or you say recent decade, growth rate of last decade, and this r dash is equal to average decrease in growth rate. Okay, so yeah, this is all about growth rate method, decrease growth rate method. And one last thing in water demand, that is logistic curve. Last thing is logistic curve method. Logistic curve method. Basically, in water demand, these three methods is most important for numerical solving point of view, and for theoretical point of view, these two method also important. So let's see, we'll discuss it also. That p is equal to, we have formula in this, that p is equal to ps upon 1 plus m, 1 plus m log nt to the base e. Okay, and where this m, where this m is equal to ps minus p naught upon p naught. Okay, and this ps have value PS is equal to, you can find PS is equal to P1, P naught, P1, P2 minus, give me a second. So 2 P naught, P1, P2 minus P1 square into P naught plus P2 whole divided by P naught P2, P naught P2 minus P1 square. Okay, so you'll calculate PS like this. And these thing that what is this PS, P1, P naught and P naught, P1, P2. So P naught is obviously, you also know that P naught is population at beginning, and P1 is population after time T1, population after T1. Similarly, P2 is population after T2, and PS is saturation population. Saturation population. Okay, so this is PS. And one more thing in this logistic curve, that is N. We also have a formula for N, that is for N we have formula, and that N is equal to 1 by T log in the bracket P naught into PS minus P1 whole divided by P1 into PS minus P naught, this to the base E. Okay, and also we have a formula for N, that 2.3 upon T1 log, basically T1, or you say T. Okay, that log to the bracket the same thing P naught PS minus here 1 into P1 into PS minus P naught. Okay, here I think it's P1. This basically it is in to the base 10. That's why you get this 2.3. Okay, this is how you get the value of N. And we also have a graph for this. Let's discuss on the next page. That graph is something like, wait a second. Yeah, give me a second. Something like this. So this is, let's say this is O or 0. This is T1. Here it is T2, and here it is, let's say, T. And similarly here let's say P1, here P2, and here P, and let's say here PS. Okay, so we have, if you join this with this with this, then we'll get and if you reset that, then we'll get a curve like this. Give me a second. you know, or something like this, kind of this type of curve, not make it properly. So it is something like this. Okay, so this is about a logistic curve, and here it is increase in population. Okay, and either it is time, log time. This is all logistic logistic curve. Okay, and this is last method in water demand for population forecasting. So this is all about water demand in environmental engineering. Soon we'll discuss its previous year questions of gate examination. Till then, do a lot of question of gate, and yeah, practice more and more so that you'll perform very well in gate examination of 2022. Okay, and till then, take care. God bless you. Thank you so much for watching this video. Thank you.